Wabarakatuh. Welcome to Wisdom International School's digital classroom for mathematics. So today we are going to start a new chapter, circles. Okay, so we are done with triangles. So hope you have all learned the theorems and the proving, and also you have completed your homework, the exercises. So now we'll start the new chapter, circles. Okay, so first let's do the introduction. So you all know what a circle is, right? So when we give a name to a circle, we name it with the center, right? If we say circle O, it means the O is the center of the circle, right? And we also know that we have to mention the radius of a circle. So now we are going to learn a new line which is called as a tangent. So we'll see what a tangent is. Okay, so now we can actually draw, if you're drawing a circle and a line in a sheet of paper. Okay, so there are three ways you can draw a line. One is you can draw a line like this. See, a circle is over here and a line is over here. Okay, they are not at all touching each other, so this line is non-intersecting line compared to the circle, right? With respect to the circle, this line is not at all intersecting the circle. Okay, so now the second kind of a line is, what if the line just crosses the circle like this? So it's actually intersecting the circle at 2 points, right? This kind of a line is called as a secant. All right, now the third one is a tangent. Okay, the tangent is a line which touches the circle at just 1 point. Okay, so that is what is called as the tangent. So about this tangent we are going to learn today. Okay, so now, so if I ask you the definition, see, I have written a definition over here. A tangent to a circle is a straight line which touches the circle at only 1 point. Okay, so tangent, see, you have only 1 point. The point of contact is just 1. Okay, so this particular line which touches the circle at only 1 point is called as a tangent. Okay, so now we have few notes about it. Let's look at these. See, there is only only one tangent at a point of a circle. So if you're talking about a circle and just a point on the circle, like if I give you a circle over here and I say that there is a point over here, and if I ask you how many tangents can you draw on passing through this point, you can draw only one line. Okay, there's only one tangent which can be drawn passing through the point on a circle. Okay, so now the second point says the tangent to a circle is a special case of a secant when the two endpoints of its corresponding chord coincides. See, if you have a circle, okay, and a secant is actually a line which crosses through the circle like this, right? So what if I draw a line whose see, this particular line from here to here is called as a chord, isn't it? So this is a chord. Now what if I draw one more chord? Okay, this is another chord. Understood? So if I actually draw a line which is joining these two chords together, so then I end up getting, see, if this is one of the endpoint of the chord and this is another endpoint. See, both this point is an endpoint of both the chords, right? Now what if I join these two endpoints together in a line? So then I end up getting a line like this, right? This is how I get, this is what is called as a tangent. Okay, so why we are learning these points is these kind of they may give you problems based on these not problems, actually the statements, okay, based on these points as your multiple choice questions. Okay, so you need to know these things clearly. Okay, now coming to the next one, the common point of a tangent and circle is called a point of contact. So now if you have a circle over here and if you have a tangent over here, the point which intersects the circle and the tangent, this particular point is called as a common point. Okay, now this is our common point and this is called as a point of contact. Okay, all right, so now let's come to this one, the last point. The tangent touches the circle at the common point. So you all know this. See, this is the common point and the tangent is actually touching the circle at this particular point. Got it? Okay, so that's what they say. The tangent always touches the circle at a common point. So they can actually frame a multiple choice MCQ questions based on these points. Okay, so you need to know this thorough. I mean you don't have to mug this, understand it well. Okay. Now come to theorem 1. So actually I want you all to write everything from the beginning, okay? From the introduction, I want you all to copy down in your notebook, okay? Just don't start with exercise. Start with the introduction. Write all the notes, whatever I have given in this thing, okay? In this page. Okay. Now come to theorem 1. Okay, so then this theorem, it's, you know, there are two theorems, only two theorems in the whole circle chapter, and they are very simple theorems. You know, you may get it for 3 marks, okay, not more than that, because they are very small theorems. Okay, so now theorem 1 says the tangent at any point of a circle is perpendicular to the radius through the point of contact. So first let's understand what it says. Okay, see, there is a tangent, you know, let's say this is a circle, okay, and there is a tangent. Okay, let's say this is the tangent. Okay, now if I draw, and this is supposed to be the center, and obviously when I draw a radius touching this particular point, this is the point of contact, and if I draw a radius like this, okay, this radius and this tangent will be always perpendicular to each other. That is what the statement says. The tangent at any point of a circle, so any point of a circle is perpendicular. Perpendicular means 90 degree, okay, to the radius. So it's perpendicular to this radius, okay, through the point of contact. Understood? So if I draw another tangent here, let's say I draw another tangent over here, then if I draw the radius joining this particular point, then this particular point and the radius, I mean this tangent and the radius will be perpendicular to each other. Understood? So this is what we are going to prove now. So let's start now. So what is given to us? We just know that xy is a tangent. Let's say, you know, there is a circle over here. See, come down. I have drawn a circle in red color. So there is a tangent xy, and O is the center of the circle. Okay. So now what all we know in this? We know that this is a circle O, and it has got a tangent which is xy. Okay, and it's touching the circle at point P. This is all we know. So we write down what is known to us. Okay, so xy is a tangent to circle O at a point P. That's it. Okay, now what do we have to prove? We have to prove that OP is perpendicular to xy. That is, these two are perpendicular to each other. Okay, this is 90 degree. This is what we need to prove. Now we will do a small construction. Okay, to prove this we have to draw a construction. See, I have written in a green pen, and the construction is also done in the green pen. Okay, so this is what we are doing it by ourselves. Okay, from the theorem what do we get? We have it, the given and the to prove is from the theorem. Okay, now the construction we have to do it ourselves. So we are just joining OQ as shown in the figure, and you can see that the Q is lying on the point XY. All right, on the line xy, sorry. Okay, so the Q lies on the line xy. Now we know that OQ is larger than OP. See, look at this OQ. OQ is this long line. This line is larger than OP. So how can we say that? See, xy is a tangent. It's been given to us, right? And a point on tangent P. And see, and this, you know, xy is a tangent. And a point on a tangent other than the point of contact will lie outside the circle. See, this xy is a tangent, and I am actually drawing a point, marking a point on the tangent. So obviously, and this particular point is not P. We know that it touches the circle at P, right? But we are marking some other point apart from P. So obviously, this OQ will be greater than OP because it's the tangent which is outside, right? See, if it turns out to be inside, let me say that, you know, I say that, you know, it turns out to be inside. Then the xy has to be inside the circle. Only then it will turn out to be inside, right? See, if I have xy over here, and then if I'm drawing a Q inside, then this is the only case when, you know, I can get, you know, this is the center O, and this could be taken as the radius. This is radius P, right? And this particular radius is larger than OQ only if xy lies inside, crosses inside the circle. Then in that case, xy will not be called as a tangent at all. It will be called as a secant. So, you know, again here we are like, you know, we don't, we know that this is not a secant. It's a tangent. So definitely the Q is going to be lying outside the circle O. Okay. So OQ turns out to be greater than OP. So now this happens with every point on the circle, right? You take any point on this circle, that's what is going to happen. So OP turns out to be the smallest side in this case, right? So this, see, now you see here, since this happens for every point on the line xy except the point P, OP is the shortest of all the distances of the point O to the points of xy. So the OP distance is the smallest, okay? So OP is perpendicular to xy. Understood? Hence proved. See, when I say that, let us say you have two lines, okay? Let me say the lines are drawn like this. Now, if I ask you what is the distance between these two lines, you will see the perpendicular distance, not the slanting distance. If I say, this is my distance or this is my distance, that's not the right way of measuring it, okay? You will see what will be the right way of measuring it. If I want to find the distance between these two, I will draw the perpendicular distance, right? It should be perpendicular. So perpendicular distance is the shortest always, correct? So since this OP turns out to be the shortest distance, we know that it's going to be a perpendicular line to xy, okay? So that's what has been proved. Okay, now based on this we get two more notes, okay? So let's say at any point on a circle there can be only one tangent. So you know this, right? If I have a circle and if I give a point over here, there could be only one tangent drawn at this particular point, not more than one, okay? Now the second point says that if I have, the line containing the radius through the point of contact is also sometimes called as normal. See, this particular line, see, when we say that this is a radius and this is a tangent, okay, let's say these two are perpendicular to each other. We always say this, right? But there is another term used for this where if we can also say that they are normal, okay? This R is a normal or T is a normal. That means it's like perpendicular, okay? So this normal word actually means it's like pointing at 90 degree. It's perpendicular, that's all, okay? Perpendicular. All right, so now you have to solve exercise 4.1. From your PDF you can just solve exercise 4.1 in your classwork notebook, okay? Also copy down all the notes given in this session in classwork notebook, okay? So I want you first to write everything whatever I have explained so far, and then after that you can start exercise 4.1. You must be having, see, those who have textbook can refer 4.1, so you finish it off. All right, so see you inshallah with the continuation of this chapter. We'll do exercise 4.2. Okay, Allah Hafiz. Thank you.